How the 2016 bleaching altered the shape of the northern Great Barrier Reef. Recent ecological upheavals on the reef have caused widespread systemic damage. Selina Ward from the University of Queensland reports. In 2016 the Great Barrier Reef suffered unprecedented mass coral bleaching, part of a global bleaching event that dwarfed its predecessors in 1998 and 2002. This was followed by another mass bleaching the following year. This was the first case of back-to-back mass bleaching events on the reef. The result was a 30% loss of corals in 2016, a further 20% loss in 2017, and big changes in community structure. New research published in Nature now reveals the damage that these losses caused to the wider ecosystem functioning of the Great Barrier Reef. Fast-growing staghorn and tabular corals suffered a rapid, catastrophic die-off, changing the three-dimensional character of many individual reefs. In areas subject to the most sustained high temperatures, some corals died without even bleaching, the first time that such rapid coral death has been documented on such a wide scale. The research team, led by Terry Hughes of James Cook University, carried out extensive surveys during the two bleaching events, at a range of scales. First, aerial surveys from planes generated thousands of videos of the reef. The data from these videos were then verified by teams of divers in the water using traditional survey methods. Finally, teams of divers took samples of corals and investigated their physiology in the laboratory. This included counting the density of the microalgae that live within the coral cells and provide most of the energy for the corals. The latest paper follows on from earlier research which documented the 81% of reefs that bleached in the northern sector of the Great Barrier Reef, 33% in the central section, and 1% in the southern sector, and compared this event with previous bleaching events. Another previous paper documented the reduction in time between bleaching events since the 1980s, down to the current interval of 1 every 6 years. Although reef scientists have been predicting the increased frequency and severity of bleaching events for 2 decades, this paper has some surprising and alarming results. Bleaching events occur when the temperature rises above the average summer maximum for a sufficient period. We measure this accumulated heat stress in degree heating weeks, DHW, the number of degrees above the average summer maximum, multiplied by the number of weeks. Generally, the higher the DHW, the higher the expected coral death. The U.S. National Oceanic and Atmospheric Administration has suggested that bleaching generally starts at 4 DHW, and death at around 8 DHW. Modeling of the expected results of future bleaching events has been based on these estimates, often with the expectation the thresholds will become higher over time as corals adapt to changing conditions. In the 2016 event, however, bleaching began at 2 DHW and corals began dying at 3 DHW. Then, as the sustained high temperatures continued, coral death accelerated rapidly, reaching more than 50% mortality at only 4 to 5 DHW. Many corals also died very rapidly, without appearing to bleach beforehand. This suggests that these corals essentially shut down due to the heat. This is the first record of such rapid death occurring at this scale. This study shows clearly that the structure of coral communities in the northern sector of the reef has changed dramatically, with a predominant loss of branching corals. The post-bleaching reef has a higher proportion of massive growth forms which, with no gaps between branches, provide fewer places for fish and invertebrates to hide. This loss of hiding places is one of the reasons for the reduction of fish populations following severe bleaching events. The International Union for Conservation of Nature, IUCN, which produces the Red List of Threatened Species, recently extended this concept to ecosystems that are threatened with collapse. This is difficult to implement, but this new research provides the initial and post-event data, leaves us with no doubt about the driver of the change, and suggests threshold levels of DHWs. These cover the requirements for such a listing. Predictions of recovery times following these bleaching events are difficult as many corals that survived are weakened, so mortality continues. Replacement of lost corals through recruitment relies on healthy coral larvae arriving and finding suitable settlement substrate. Corals that have experienced these warm events are often slow to recover enough to reproduce normally, so larvae may need to travel from distant healthy reefs. Although this paper brings us devastating news of coral death at relatively low levels of heat stress, it is important to recognize that we still have plenty of good coral cover remaining on the Great Barrier Reef, particularly in the southern and central sectors. We can save this reef, but the time to act is now. This is not just for the sake of our precious Great Barrier Reef, but for the people who live close to reefs around the world that are at risk from climate change. Millions rely on reefs for protection of their nations from oceanic swells, for food and for other ecosystem services. The conversation this research leaves no doubt that we must reduce global emissions dramatically and swiftly if we are to save these vital ecosystems. We also need to invest in looking after reefs at a local level to increase their chances of surviving the challenges of climate change. This means adequately funding improvements to water quality and protecting as many areas as possible.